Exam 2 is tomorrow. The rooms have been announced on a Canvas page, but there they are just in case. It covers all of Chapter 18. Quiet! Quiet, please. Okay, it covers all of 18, 19, except the material on metal ion ligand chemistry. And so that's the last part of the chapter. I didn't get a chance to get to that. Oh, I'm so sorry. But it goes up through the stuff on solubility product equilibrium. I want to hit a couple more topics on that, and then we'll stop. All right. Last time we were talking about factors that affect the solubility of precipitates. So last time we left off with this kind of problem. It's called the common ion effect problem. There will be a problem like this on exam 2. Asks you to compare the solubilities in pure water versus a salt with a common ion. What's the common ion? Fluoride. Common to both the precipitate and to the salt that you added. Now, in working this problem, you have to understand, of course, that sodium fluoride is a strong electrolyte and therefore dissolves completely into sodium ions and fluoride ions, and that calcium fluoride is a weak electrolyte and, in fact, dissolves only a tiny bit. And we said that it's going to be less soluble here in that beaker, and it's going to be less soluble because of a simple application of the principle of Le Chatelier. We've got this calcium fluoride solid, not very soluble, trying to spit out a little bit of calcium and a little bit of fluoride, but the soluble sodium fluoride assures that there's a whole bunch of that fluoride floating around in that solution. So what does Le Chatelier tell us? Le Chatelier tells us if you add a product of a reaction, the position of equilibrium shifts back to the left. So by attempting to dissolve it in that 10th molar sodium fluoride, we stressed it relative to the pure water case. So the position of equilibrium goes back to the left. Simple kind of a problem that you might encounter on the exam. Asks you to compare those solubilities. So it's a common ion effect example. It says calculate solubility of silver chloride in water and 0.1 molar sodium chloride. So the water one is easy. We say for either one That's the reaction that we're dealing with, that little bit, tiny little bit of dissociation of that stuff. How do we know it's a tiny little bit? Well, the KSP is a tiny number. So we write KSP is the equilibrium concentration of silver, equilibrium concentration of chloride, and that is 1.8 times 10 to the minus 10. So, in the pure water case, we say that the solubility is equal to the concentration of silver, and it's also equal to the concentration of the chloride. Because in the pure water case, for every 1 silver chloride that dissolves, I get 1 silver and 1 chloride. So the solubility is equal to the silver is equal to the chloride. So that means that KSP is S squared if we just plug those S into here and S into there. And so that means that S is equal to the square root of the KSP for this simple example. And when I do that calculation, I get 1.34 times 10 to the minus 5 molar. So there's your proof that it's a weak electrolyte. Now, we predicted, or Le Chatelier, our friend Le Chatelier predicted that when we've got this soluble common ion, it's going to push the position of equilibrium back to the left. So we should calculate a lower solubility. So we could say in the 0.1 molar sodium chloride, what we could think about is that the chloride total, so in this solution now we've got to think about it, there are 2 sources of chloride. There's chloride that comes from the silver chloride dissociation, according to this reaction right here. And there's chloride because we threw in soluble sodium chloride. So we might write the chloride total is the chloride from sodium chloride plus the chloride from silver chloride. So there's a total chloride in that solution. It's the chloride you added from the sodium chloride plus the chloride from the silver chloride. But since this is a weak electrolyte, that is negligible. Again, it's going to be a big number, 0.1 molar, and a very small number. How do I know it's a small number? Even in pure water, it was a very small number. And it's about to get an even smaller number. And so, yes, this is true that there are 2 sources of chloride in this solution. But the contribution from the weak electrolyte is negligibly small relative to the contribution from the strong electrolyte. That greatly simplifies the problem. That takes it from a quadratic to a simple linear equation. Because then you can say, we write the same KSP, which is our, where is that, 1.8 times 10 to the minus 10, is the concentration of silver. So far, nothing changed. But again, for this example, for every 1 silver chloride that dissolves, I get 1 silver ion. And so the solubility in this example is equal to the concentration of silver. Now, you also get 1 chloride, but there's a heck of a lot more chloride in the solution than just that. So the only thing I'm absolutely certain about is that for sure For every one of those dissolves, I get one of those. And therefore my solubility has to be the concentration of silver. And once I recognize that, it all becomes crystal clear. So then we write that KSP, which is concentration of silver times concentration of chloride, we now recognize that that's the solubility times the concentration of chloride. But we also know the concentration of chloride because we're told that there's 0.1 molar sodium chloride, therefore there's 0.1 molar chloride. So that makes life really simple. Boom. And that's our. And so now you've solved for the solubility in this case. So there you go. Le Chatelier predicted the solubility would be less in the solution of the common ion. And indeed it is, because in pure water, we got 1.3 times 10 to minus 5 molar for the solubility. But in the sodium chloride solution, we got 1.8 times 10 to minus 9 molar. So it's 4 orders of magnitude less soluble in the presence of the common ion. All right. So the principle of Le Chatelier is one of the kernel's core concepts. You can understand that now because almost, every week something comes up that involves Le Chatelier. So if you get Le Chatelier fixed into your head, you can solve a whole bunch of chemical problems by just asking this question. Have I stressed the reaction? And if so, what will it do to minimize that stress? A whole bunch of chemistry can be solved that way. So that's why Le Chatelier, who we just mentioned, is one of the kernel's core concepts. All right. So we're talking about things that affect solubility of weak electrolytes. Many weak electrolytes, not all, but many. pH may affect solubility. And there are many examples of why that might be. So for example, if you're looking at this precipitate, our friend lead hydroxide, very pretty salt. It's bright yellow. If you ever see it, it's quite impressive. Lead salts often have yellow color. Very nice. But that's a weak electrolyte. So we get a little bit of this. And a little bit of this. And so if I had the KSP, I could calculate the solubility of that salt. Now what if I had that solution, it's at equilibrium, I'm dissolving that salt in pure water, nothing tricky, nothing up my sleeve, but a hairy arm. Now what if I took that system at equilibrium and I made the solution basic? What would happen to the solubility of this weak electrolyte? Yes, sir? It would be lower. So I made the solution basic. What does making the solution basic mean? It means increasing the hydroxide ion concentration, right? Again, we come back to our pal Le Chatelier. It says if you make the solution basic and therefore you increase the concentration of hydroxide, well, you will shift the position of equilibrium back to the left. So any sort of salt involving hydroxide will have that characteristic that it would the solubility is very pH dependent, because what you mean by varying pH is varying the concentration of that hydroxide, which is a product of that reaction. There's another fun kind of example. So this is anybody ever go to the eye doctor? Go to the eye doctor? Who goes to the eye doctor? Come on, hands up. So you know how when you're at the eye doctor, he or she goes, is it better here or here? You know what I'm talking about? Here or here? Here? It's like you want to strangle this guy. So that's what I'm doing now. I'm doing the chemical equivalent here. I'm going to again give you two beakers and ask you which the salt is more soluble in. So now we got our friend here, calcium fluoride again. I like calcium fluoride, and this is pure water. And seem to be breaking chalk today. I don't know what's going on. And there's our calcium fluoride again. But this is 10th molar HCl. Okay, so now I'm going to do the eye doctor thing. Is it going to be more soluble here or here? It's going to be more soluble there. Very good. And why is that? Because fluorine is a base. Very, very good. So yes. And again, it just comes right back to Le Chatelier, our pal Le Chatelier. I'm going to write a song about Le Chatelier. Le Chatelier. It's like a yodeling song. Le Chatelier. Okay, it was just an idea, okay? I'm just, brainstorming here. Yeah. But here's the way to think about it. Let's take it stepwise. Let's let the reaction reach equilibrium in pure water, in this beaker right here. And then let's simulate this condition by dropping in some concentrated HCl to make it 10th molar. So we're going to do it in two steps. First, we got the pure water case. So in the pure water case, this reaction reaches equilibrium. It produces a certain amount of calcium and a certain amount of fluoride given by the KSP. Now we're going to simulate this case right here by dropping in some concentrated HCl and getting the concentration up to 10th molar. Now, what that means is that you added a whole bunch of hydronium ion. And that hydronium ion will find that fluoride and make HF. And so now we're stressing the reaction in a different way. We're stressing this reaction by decreasing the concentration of a product, because that product is getting consumed by the acid. And so Le Chatelier says if you stress a reaction by removing a product, then the position of equilibrium has to shift to the right. And so yes, the answer is correct. More soluble here. And again, Le Chatelier's principle helps you understand why that is. But also I get back to this notion that you've got to remember these chemicals. You have to remember that fluoride is a weak base, and that's the key to understanding this problem. So building up vocabulary. Now, so far we've approached solubility product equilibrium from the point of view of we got the solid and we're going to let it dissociate and reach equilibrium. I want to turn it around now and maybe talk about something that's a little more practical aspect of it. And that is that if you have a metal ion in a solution, let's say you've got this solution and it's got in here it's got silver ion and it's got sodium ion, maybe it's got some potassium, maybe it's got some calcium. So it's water with all those ions in it. Now, silver is valuable. Silver is a valuable metal. It's a coinage metal. There are people who invest in silver. I invest in silver, invest in gold. Most of my money is invested in groceries this month. Just trying to... Anyway, so there's that beaker. It's got all four of those ions in there. I might want to collect that silver ion. I might want to get that out of there because it's valuable. I'm not too concerned about what happens to the other ions, but I might want to collect that silver ion. So you say, well, great. Just add some aqueous chloride. And indeed, if you do that, you will start to see this white silver chloride precipitate rain out of the solution. It's fun to watch. It just comes raining out of the solution. Beautiful, pure white precipitate. So you know it works because what you're doing is you're taking the silver that you want, that valuable thing, and you're adding chloride, and boom, you're making silver chloride. Sometimes in chemistry we put a down arrow, meaning a precipitate formed. You don't see that all the time, but it helps me think about this reaction if I can visualize that precipitate raining out of the solution. So now, being greedy, I want to get all of it out. You know, I want to collect this silver. I want every little nano, pico, attogram I can get, right? And so the question then becomes, well, how much chloride do I got to add to get it all out? This is a valuable metal. I want to get it all out. How much chloride do I got to add to get it all out? And the answer is, so that's, you know, the key question. Key economic question. And the answer is, you can't get it all out. Now, what do you mean by getting it all out? It means if you wanted to get it all out, you'd have to believe that the concentration of silver in that solution is 0. I mean, that's what getting it all out would mean, right? But you can't achieve that. Why can't you achieve that? You can prove it to yourself mathematically. Let's just write KSP is the concentration of silver times the concentration of chloride. And you say, great, so now I want to solve for concentration of silver. Concentration of silver is equal to KSP divided by the concentration of chloride. Yeah, is that right? And I just said I want to get it all out. That means that's got to be 0. What's the chloride ion concentration got to be?
0, which is not positive. I mean, you can divide by 0.
Mathematically. It would have to be infinity. So the only way to get to silver 0 is to have an infinite amount of chloride. So that's the bottom line. You can't get it all out. But you can specify any concentration that you want. Meaning, I could say, oh, I'm not greedy. I'll leave behind 10 to the minus 6 molar. Gosh, 10 to the minus 6 molar, that's hardly any at all. Then you think, no, I'm way greedier than that. I only want to leave behind 10 to the minus 9 molar. A nanomolar. The kernel says that's a very low concentration. I can live with that, leaving nanomolar behind. You get up the next morning and you go, no, I'm even greedier than that. I want it 10 to the minus 12th molar. That's all I want to leave behind. So the answer is you can't get it to 0. You got to leave something behind. It's up to you how much you want to leave behind. And so if we said, let's not be real greedy. So let's say, here's what I want to do. I finally decided not to be real greedy. So there was my solution with my silver. And I'm going to add the chloride. And I'm going to say, all right, if at the end of the day, when that's all done, the concentration of silver left in there is 1 times 10 to the minus 9 molar, or 1 nanomolar, then I can live with that. I mean, for gosh sakes, that's as close to 0 as you might want to get. So then, so what do we do then? So then we can solve our problem again. We can say, I want to get that silver down to 10 to the minus 9 molar, so I write KSP is what? 1.8 times 10 to the minus 10, right? It's equal to the concentration of silver, the concentration of chloride, and I just said I want that thing down to 10 to the minus 9 molar. Boom. So now I can simply solve for the concentration of chloride that I need to do that. And that would be my KSP divided by 10 to the minus 9, or 0.18 molar. So, what did we just learn? By controlling the chloride concentration, I can adjust the concentration of silver remaining in that beaker to any value I want. But you can see that I said I could live with it being 10 to the minus 9 molar. And in order to achieve that, I got to have a pretty high concentration of chloride. I got to dump a bunch of chloride in there and get the concentration up to 0.18 molar to drop it down to 10 to the minus 9. But what if I was even greedier? What if I wanted 10 to the minus 12? I couldn't sleep at night unless I got it all out to the point there was only 10 to the minus 12 molar. The problem now is you're running up against the solubility of sodium chloride. So the solubility of sodium chloride in water is about 5 molar. That's about it at room temperature. And so you might be able to get it an order of magnitude lower. So if that was 1.8 molar, then that would get you down to 10 to the minus 10 left in there. But you're not going to get to 18 molar because it's not that soluble. And so maybe around 10 to the minus 10 is the best you're going to practically do. But, you're leaving 10 to the minus 10 moles per liter left. I think you're doing pretty good here. Now, all right. so what do we got now? Yes. Yes. Did that. Yes. Okay. Right. Now, here's a more interesting problem. More interesting kind of problem. So, this comes under the heading, by the way, of chemical separations. Yes?
When you're adding a material, how does it reacting with the Na or the K or the Ca?
What's that?
If you're trying to get out the silver, how do you prevent the Cl from reacting with the Na or the K or the Ca+?
Good question. So the question was, I put in that beaker 4 ions. I think it was sodium, potassium, calcium, and silver. And the question was, well, how doesn't the chloride affect the sodium, potassium, calcium, and silver? Or sodium, potassium, and calcium. And the answer to the question is again, I stacked the deck. Silver is the only one of those cations that forms an insoluble chloride. So there's sodium ion in there. I can throw all the chloride I want in until I get up to above 5 molar. So sodium chloride soluble. It's not, adding chloride's not going to affect its solubility. Same deal with potassium, same deal with calcium. So basically, the concept is if I want to remove a specific ion from a solution, I've got to choose a precipitating reagent that only goes after that ion. That's the concept. I want that precipitating reagent to be really, really smart. It ignores all these other ions in the solution and only goes after the ion I want it to go after. And in this example, that was easy because of all those metal ions, only silver formed an insoluble chloride. That's a good question. I'm glad you asked that because sometimes I think these things are obvious, and then, as it turns out, they're not obvious. It's never obvious, Chuck. All right. So here's a more interesting kind of problem. So, So this comes under the heading of chemical separations. I have a mixture of things. I want one specific component of that mixture. I want to take the rest of that mixture and bury it in a landfill in northern Kentucky. So this comes under the heading of chemical separations. Got a mixture, want one specific component of that mixture, not too concerned about the rest of it. And metal ion precipitation is a very good way to do that for metal ions. Now, here's another way to think about this problem. I got a solution. It's 10 to minus 3 molar. 10 to minus 3 molar in tin 2 plus. And 10 to minus 3 molar in calcium 2 plus. Now, what I want to do is I want to take this beaker that contains both of these. There's that beaker. It's got both of those cations in there. And now I'm going to very carefully add a basic solution. I'm going to very carefully add, for example, sodium hydroxide. So both of these ions form insoluble hydroxides. So the question is, by carefully dropping in the sodium hydroxide, can I get one of those ions to precipitate and leave the other one up in the solution? So again, a chemical separation. And as it turns out, what's going to happen is, for the reasons I'm about to explain, when you drop in the hydroxide, the tin precipitates out as the tin hydroxide. And if you're careful, the calcium remains in the solution. So by very carefully controlling the hydroxide ion concentration, I can get all the tin to rain out and still have the calcium floating happily in the solution. I can separate these two metal ions. So how do we know that's true? We know that's true by comparing the solubility product constants. So both tin and hydroxide both tin and calcium form insoluble hydroxides. So we can write it this way. And that KSP is 1.4 times 10 to the minus 28. So that's a really insoluble material. Whereas calcium hydroxide is also a weak electrolyte, going to calcium 2 plus aqueous plus 2OH minus aqueous. But that KSP so big important clue just got laid on you. Big important clue, yeah.
Isn't calcium hydroxide a strong base though?
Yes, but it's quite insoluble. But okay, just bear with me, all right? So first thing to note, yes, both of these form hydroxide precipitates. But key thing, the huge difference in KSPs. Huge difference. What's that tell you? That tells you tin hydroxide is way less soluble than calcium hydroxide. Key conclusion from the KSPs. Tin hydroxide is way less soluble. So now we can understand why I predicted that if I add hydroxide, this reaction will start happening. And the tin will rain down. It will rain down because it is the least soluble. And if I stop adding hydroxide, I can get all the tin out, or at least I can get the tin to any value I specify, and leave all the calcium in. Let's prove that case. So, again, we've already said we can't get all of anything out. But I want to separate these two metal cations. So let's just say so again, I can't drop it to 0. I'm just going to pick 10 to the minus 9 and say, just like in the last example, that's getting it all out. So I can say, fine, KSP is equal to the concentration of tin times the concentration of hydroxide squared, which is what I say, 1.4 times 10 to the minus 28. All I got to do is plug my 10 to the minus 9 molar in there and solve for the hydroxide ion concentration. So I said I want to drop the tin concentration to 10 to the minus 9. Just like in the last example I worked, same idea. I'll plug that 10 to the minus 9 in, and I'll solve for hydroxide. So to drop concentration tin 2 plus to 10 to the minus 9 molar, if we do that calculation, we need concentration hydroxide is 3.7 times 10 to the minus 10 molar. So we don't need very much hydroxide at all. If we get the equilibrium concentration hydroxide up to that concentration, we drop the tin down to 10 to the minus 9. Now, the final question to ask is, has any calcium precipitated? And you can answer that question by writing QSP. So QSP in this example is the concentration of the concentration of tin, the concentration of calcium, it's concentration of hydroxide squared. Now, this is QSP. What do I know? I know that that's 10 to the minus 3 molar because that was given. And I'm saying when I get up to 3.7 times 10 to the minus 10, so now I'm just at the point where I got all of the tin out. What you're going to find is that QSP is much, much, much less than KSP. I don't have the number worked out, but again, what am I doing here? I said I want to drop all the tin to 10 to the minus 9. That was easy. That was the first part of the calculation. That's the hydroxide I need. That's the hydroxide ion concentration I need. Now I asked a related question. At that hydroxide ion concentration, has any calcium precipitated? I figured that out by writing the QSP expression. 10 to the minus 3 is the given concentration of calcium, and that's the concentration of hydroxide. Somebody do the math here for me, will you? What is this number? What is 10 to the minus 3 times 3.7 times 10 to the minus 10 squared? Come on, you can Google that. But the bottom line is what you're going to find out is that this QSP is much, much less than KSP. And so, what does that tell you? It tells you that no calcium hydroxide will precipitate. When? 1.37 times 10 to the negative 22 is 1.8 times 10 to the minus 10. So key, fundamental, important point that comes out of this discussion. If QSP is less than KSP, you don't get a precipitate. Very important concept to get in your head. If QSP is less than KSP, you don't get a precipitate. You haven't got the concentrations up high enough. And so that's what we just discovered. When we got the concentration of hydroxide just right to get the tin down to 10 to the minus 9 molar, we plugged that concentration in there. We plugged the concentration of calcium that we were given. That's QSP. That QSP was calculated for us at roughly 10 to the minus 22nd. That means those concentrations are way too low. You can't do this. That won't happen. High enough. You'd have to get orders of magnitude higher. Yes? What?
It was originally
3.2. Sorry. gave you hydroxide. Okay, so very important fundamental point there.
This won't be on the test though, right?
Yes,
Oh, I thought this was the metal stuff.
this is not the metal. That. This is not, repeat, not soluble. That is on the test. That's why I wanted to tell you today this stuff. And again, we got behind because of the hurricane day that messed with my schedule. Okay, that's all I wanted to say today.